This study aims to implement different swarm algorithms by using crazy-fly quadcopters and a localization system through OptiTrack for future use in disaster response operations. The use of unmanned aerial vehicles in emergency situations has received a lot of attention due to the advantages it presents, such as quicker response time, the ability to reach areas that are normally difficult for people to access, and the removal of the risk presented by those areas to the people undergoing emergency operations. Search and rescue operations benefit the most from the use of UAVs. Currently, UAVs are already being used for disaster response. The problem with majority of the current systems being utilized is they are single robot systems. Multi-robot systems can cover more ground in less amount of time, which is an important factor in disaster response. Single robot systems are also more prone to failure. Multi-robot systems are able to function even with the failure of one of their agents. For more optimal search and rescue operations, more UAVs should be used, but at the same time, a proper control method should be used on those UAVs. One of the more popular methods of control for a large amount of UAVs is the application of swarm intelligence. Swarm intelligence is based from the characteristic exhibited by animals. Certain animal groups such as insects, birds, and fish possess swarm intelligence, which makes them more versatile, capable, and robust. Swarm robotics is a field in robotics in which multiple robots utilize the swarm intelligence to perform certain tasks and objectives. This intelligence enables robotic systems to create ways to perform tasks faster and efficiently through coordination despite having a large number of members. Examples of swarm intelligence are aggregation, foraging, formation, tracking, and the sweep cleaning protocol. A distinct feature in the design and analysis of both swarm and swarming algorithms is the simplicity of the agents. In this study, swarming algorithms were implemented using quad rotors, specifically Crazyfly 2.0. The implementation of the swarming algorithms presents many benefits in the future. The use of quad rotors rather than other forms of unmanned aerial vehicles and wheeled mobile robots allows the system to exploit its agility and flying advantage. This allows swarm to operate in tighter and more cluttered environments. The system envisions a quad-rotor swarm to be used to perform tasks in times of emergency such as search and rescue, especially in environments where there is restricted human access, potential human risk, or the need for crucial response. Each member may be tasked to search a different area and send alerts to other agents of the swarm once a trigger is found. A quad-rotor may alert the team to stay away from unfavorable areas and move towards favorable areas, such as places where it detects people, in terms of search and rescue. The emulated environmental factors for this system may be substituted for real-world environments and allow the swarm to react accordingly. Ultimately, the overall system presented in this paper may be used as an initial test bed for swarms with environmental consideration. Motion capture, also known as mocap, is defined as means of measuring the position and orientation of an object moving in space. Basically, mocap converts live performance into a digital performance. One popular type of mocap is the optical motion capture. Optical mocap makes use of cameras as a mean of capturing or detecting every motion inside a specified area. The mocap used for this project is OptiTrack. Reflective markers are attached to the quad rotors for detection and for getting its coordinate. Through these reflective markers, the OptiTrack can gather the coordinates of each quad rotors and pass it on the base station for processing. The base station will process the data gathered from the OptiTrack to determine the next movement of the quad rotors. This algorithm was derived from the algorithm made by Altshuler and was modified to fit the desired application. In this algorithm, the agents, which are the quadcopters, will locate and clean the contaminated tiles inside the perimeter of the target area. The algorithm will only clean its current position only when the cell is inside the area and there are no other agents present in its 4 neighbors. The quadcopters will continue to move around the target area until they are in a contaminated cell. This algorithm automatically allows the agent to go to the next contaminated tile when there is only one contaminated tile connected to it and if there is no other agent on that tile. In addition, when the quadcopter's current position are located in the perimeter, it will turn 90 clockwise until an adjacent contaminated tile is determined, and if that tile does not contain an agent, the current agent will move forward. In the execution of the algorithm, certain perimeter cells aren't permitted to be cleaned. This is due to either the agent having an adjacent agent or the current cell is considered as a critical point. Critical points are defined by Altshuler as cells that, when removed, causes the discontinuity of the area or separation of the area into multiple smaller areas. Lastly, in this algorithm, it does not allow 2 agents to coexist in a single cell. Coexistence in a single cell introduces the risk of collision, which is not permitted. There are 2 types of area created in this project, the dynamic and the static area. Both areas vary on the width and length depending on the input of the user. The main purpose of the graphical user interface is to provide a visual representation of the algorithm's performance and the predicted flight path of each agent. This was made using the Python programming language. Also, the graphical user interface provides a representation of the contamination and the spreading that occurs, which is dictated by the time step it will spread. In the graphical user interface, the contaminated tile is represented by a black tile, while white tiles represent the uncontaminated tiles. The agents are represented by 4 distinct color shades for it to be easily identified. The static area sets the whole target area as contaminated. The dynamic area, on the other hand, allows the user to input one target cell that serves as the starting point for spreading. This target cell is expected to spread consistently at a given time, specifically called spread time. Spread time is set to control the spreading of the contaminated cells and is determined through time steps. At a specific spread time, the target cell starts to spread on its adjacent cells, forming a perimeter of contaminated cells. The spreading will continue of the formed perimeter also through its adjacent cells until it disperses on the whole target area. The main system framework is composed of 3 parts. These 3 parts are the motion capture cameras, computer base station, and the quadcopters. It can be observed that software and hardware components interact and communicate with each other. The localization of each quadcopter to be used was made possible using OptiTrack motion capture. The coordinates given by the OptiTrack will be transmitted and processed in the computer base station. The computer base station is responsible for the processing, computing, and data transmission. The computer base station has 2 main components that operates independently. These 2 parts are the area generation algorithm and the main sweep algorithm. The area generation algorithm is responsible for creating a dynamic area in which the spread time and initial contamination is set by the user. The sweep protocol, on the other hand, is responsible for creating commands in which the quadcopter will follow in order to finish its objective. The current location of the quadcopter will be verified either contaminated or not by checking the current cell position whether or not it is included in the contaminated area through an inquiry to the area generation algorithm. The flight of the quadcopter will be governed by a 3-layer PIDE control. The communication by the base station to the quadcopter can be accomplished using a Crazy Radio USB dongle and supported by a Crazyflie client. The quadcopter control framework will be uniform to all Crazyflie quadcopter in order to depict swarm intelligence, specifically sweep algorithm. The capacity of the quadcopter system can accommodate n number of quadcopter depending on the system processing of the ground computer station and the number of motion capture cameras available. In cleaning static areas, both positioning and number of agents have an effect on the clean time of the protocol. Placing the starting positions of the agents on the corners of the area yield a faster clean time compared with positioning them on the perimeter or inside of the area. This is most noticeable when already using 4 agents where there is, On average, a 22.16% decrease in clean time. Although this is only applicable when dealing with more than one agent. From the data obtained, it can also be seen that adding more agents also decreases the clean time. The negative effects on the clean time were observed by adding quadcopters. The highest decrease in clean time was observed when from using one agent, another agent was added. The effect of adding agents gradually declines as the number of agents increases. Once again, there is a large deviation from the results obtained using one quadcopter when compared with multiple quadcopters. At smaller initial areas, increasing the number of quadcopters has a significant effect on the reduction of spread time. Subsequent additions have lesser impact. From the graph, at an initial area of 67 and upwards, the plots using multiple quadcopters converge. This could be attributed to the fact that the spreading that occurs at this initial area is too large for the quadcopters to handle. Additional tests making use of more quadcopters may show a different trend, but that is above the focus of this paper. The simulation results of the sweep algorithm proved its effectivity since the objective of the algorithm was achieved. It was also proven that increasing the number of agents improved the performance of the algorithm for both static and dynamic area. It was also observed that the algorithm's performance was dependent on the agent's position. For static areas, placing the agents at equidistant locations yield optimal performance. However, there are instances where the algorithm fails due to the modifications made. Though the problem exists on static areas, the spreading on dynamic areas solved the issue. Even though the spread time could help solve the problem encountered in static area, this also has drawbacks. The spread time is relative to the number of agents. As the number of agents decrease, the spread time must increase. Since randomness is more evident on dynamic areas, the agent's position cannot be related to its performance. The factor that can be related is the number of agents used. In disaster response operations, static areas can be fixed locations for search operations. Dynamic areas, on the other hand, represent locations where the scope of the area increases over time due to the movement of targets such as those for rescue operations or due to the spreading of fire. Being able to cover both static and dynamic areas at maximum efficiency and least time will increase the chance of success of disaster response operations.